Now here, let's take a problem where I have to involve the solid structures. So the problems we are going to practice on how different solid structures are combined and how we find the lateral surface area or the curved surface area or the total surface area or even the volume of the solid structures. Say for example, I have taken this missile or a diagram. Now the question is, find the amount of material used to make the missile of following dimensions. Also find the capacity of the missile is the question. Now here there are two different questions asked here. Find the amount of material used to make the missile is a question related to areas, and find the capacity of the missile is a question related to finding the volume or the space. So the question here is about finding the area and volume of this solid structure. Now clearly, when I see there are three basic structures, solid structures, which I identify in this missile. Here the upper part is a cone, the middle part is a cylinder, and the third part is a hemisphere. So let's see more clearly on how we get the different solid structures. Initially I get a cone, this is the cone, and next I get a cylinder, and finally I get the bottom part, which is a hemisphere. Is what I get when I divide each of them into this, this, and this. Now let's find the areas and volumes of each of the solid structures and combine, where I get the answer for the entire missile. So here with this cone, let's see what exactly is the radius of this cone. Now as I see the main diagram with its dimensions, I clearly see that the radius is not given, but indirectly the whole width of the missile is given to be 6 meters. So radius is exactly half of the 6 meters, that is 6 by 2 is the radius, which is 3 meters. So radius of the cone is 3 meters and the height of the cone is 4 meters is what we get. So 3 meters and 4 meters is the radius and height respectively for the cone. Let's come back to the cylinder. As I see here, the radius of the cylinder is same as the radius of the cone because it is vertically straight missile. Therefore, the radius of the cylinder also is equally 3 meters. Now next, let's see what is the height of the cylinder on the hull. So in order to find the height, initially I'm going to take the hemisphere because this helps me in finding the height of the cylinder. So if I take the hemisphere, I see that the radius of hemisphere is also 3 meters because each of the radius are equal for the cone, the cylinder, and the hemisphere. Now as I see that I get the hemisphere here, out here, like this, then in this case I observe that the radius out here is exactly the radius out here, because each of the radius is equidistant from the center to any of the point on the hemisphere. So this and this will be same. The depth of the bowl, what we have discussed, will be same as this. So this height is nothing but 2 meters out here. Therefore, this being 4 meters and this being 2 meters and this whole thing being 21 meters gives me the height of the cylinder as 21 minus this gives me the height of the cylinder. Therefore, height of the cylinder is 21 minus 4 plus 2 is what I get the height. This added with this and subtracted from 21 gives me height of the cylinder. Therefore, 21 minus 4 plus 2 gives me 21 minus 6. 4, 5, 6. Oh, this is radius is 3, it's not 2. The radius is 3. Therefore, 21 minus 4 plus 3, which is 21 minus 7, and that is 14 meters, is the height of the cylinder. So like this, the minimized information given need to be extracted with the maximum possible information which can be extracted out of the least dimensions given for the missile. Therefore, with this, I find each of the radius height, and the radius for 3 different solid structures, where I need to find this areas and volumes respectively for each of them. So once I got, initially to start with the cone, let me find the surface area of a cone, because initially it's about the amount of material used to make the missile. So for a cone, I have only CSA which I need to find, because the base is not using any material. Only the curved surface is using the material for the missile. The inside part is hollow. Therefore, the curved surface area of a cone is pi RL, which we have already discussed as a formula. Now, the radius here is 3 and the height here is 4 meters. Therefore, the slant height is something which I need to find using the right angle triangle, because it's a right circular cone, L 3, 4. Therefore, L square is 3 square plus 4 square. Using the Pythagoras theorem, I get L square as 9 plus 16, which is 25. That implies L is 5 meters. Therefore, the slant height of the cone is 5 meters using the Pythagoras theorem. Therefore, substituting here, I get pi RL, which is 22 by 7. Because the question doesn't mention about anything, I can use pi as 22 by 7. Until and unless mentioned in the question specifically. And the radius, which is 3 times the slant height, which is 5. So 5 3 is 15, 15 2 is 30, which is 30, 330 by 7, which is approximately 7 4 28, 50, 7 times 49, tens, 7 ones. So this approximately gives me 37 fours, 47.14 meters square. So this is the answer for the amount of material I have to use in making the conical part. So this is only for the conical part, the amount of material which I am going to use for the top surface. Similarly, I am going to use the same concept in finding the amount of material I use in making the cylinder. To be continued. Next, let's find for the cylinder. So I take the cylinder and I find the area. As I clearly see that I have only the curved surface area which I need to find for the cylinder, because the upper and the lower part of the cylinder are not considered in making the missile. Only the curved part is taken into consideration. Therefore, the TSA doesn't come into existence in case of this cylinder of a missile. So the amount of material I use to make the cylindrical part of the missile is the indirectly curved surface area, which is 2 pi RH, using the formula. Now, as I know the radius and height, I substitute 2 times 22 by 7 times the radius, which is 3 meters, and the height, which is 14 meters. Therefore, this on simplification gives me 7 times 2, 3 2s are 6, 6 2s 12, 12 2s 24, 12 2s 24, 25, 26 meters square. So the amount of material I require to make the cylindrical part of the missile is 264 meters square, is how I understand the concept. And lastly, I need to find the amount of material I require to make the hemispherical part of the missile. So let's see how we can do for the hemispherical part of making the missile. Now let's take the third part, that is a hemisphere. Now in the hemisphere, as I see that here also I don't have the TSA considered, because the internal part of the circular region doesn't come into account for making the missile. Therefore, the amount of material I require for making the hemispherical part is clearly, again, the curved surface area. Now, we all know that the curved surface area of a hemisphere is half the curved surface area of a sphere, that is 2 pi r square, is how we obtain for a hemisphere. Now, since the radius is 3, on substitution, I get 2 times 22 by 7 times radius is 3 square. Therefore, 9 2s 18. 18 times of 2, 36. 396 over 7, which on division approximately gives me the value 7 5s 35, 46, 7 6, 42, and 40, 7 5s 35, and 57 sevens. 7 5s 35, 46, 42, 40, 35, 57. Approximately I get 56.57 meters square is the area of the hemispherical region I require to make the missile. Now next, I'm going to add up all the three materials, that is the cone and the cylinder and the hemisphere, and hence I get the total amount of material I need to make the missile. So let's see what is the total material I require for making this missile with the following dimensions. Therefore, the total amount of material is obtained. Total amount of material required to make the missile is nothing but the surface area as obtained for the cone. We got the surface area as 47.14, and for the surface area of the cylinder, which we obtained as 264 meters square, and then the surface area of the hemispherical region, the third region, which we obtained as 56.57, is what we get in addition. So we need to add each of them, and then we get the answer. 264 and 56.57 gives 11, 5, 6, 7, and 10, 17, 10, 15, 16, 367.71 meters square is the amount of material I need to use in making the missile. So this many meters square of material is required in area wise to make the following missile. Now the question comes on how the second question is answered in terms of each of the regions. The question here is, find the capacity of the missile. The capacity is understood as clearly the volume of the missile. So when I want to find the volume of the missile, is nothing but volume of the cone plus volume of the cylinder plus volume of the hemisphere. When added up, gives me the total volume of the missile. So let's find each of the volumes respectively. So the volume of the missile, or the capacity of the missile, is nothing but the volume of cone plus volume of cylinder plus volume of hemisphere. So each of the volumes, when I add, I get the total capacity of the missile. So coming with the volume of the cone, we all know that this is 1 by 3 pi r square h, which we have taken as the derived formula, and volume of cylinder, which is pi r square h, and volume of hemisphere, which is 2 by 3 pi r cube. Remember, this height is different from this because this is height of the cone and this is height of the cylinder. They differ, though it is h here. So on substitution, I get 1 by 3. Now assuming pi is common, I take pi common and then simplify with the substituted values. 1 by 3 times r square, which is the radius, is 3. So 3 square times of h, which is 4 meters for the cone. So I get this to be 4. Then I get this to be r square h, where the radius is 3 and my h is 14. So 3 square times 14 is what I get here. Similarly, for this hemisphere, I get 2 by 3 times pi, which is taken out, times r cube, which is 3 cube, is what I get when I simplify for each of the volumes. Now let's simplify this. One of the 3 gets cancelled and one of the 3 gets cancelled as square. Therefore, rearranging and simplifying further, I get this to be 4 3s 12 plus 9 times of 14, 9 4s 36, 9 1s 126. And similarly, I get this to be 9 2s 18 is what I get. Now simplifying this further, I get this to be 28, 29, 30, 156 pi, which can be simplified using the pi value, or this is simply this many meter cube. So the capacity of the missile is 156 pi meter cube in making the complete missile. The space occupied is 156 pi meter cube. So this is how we do many problems in mensuration, where the combined structures are divided into the solid structures, and then we find separately the areas and volumes combined respectively for each of them. And once we find separately for each of the areas and volumes, we club them together, and finally we get the areas and volumes of the desired combined structures, the missile being one of the example. Now let's see a problem as an activity. Now this is a problem based on conversion of solids. That is, say for example, a cube of side 3 centimeters. Let me assume this to be a cube of each side as 3 centimeters is filled with water. I filled this cube of 3 centimeters with full of water. Then the water is then poured from the cube into a cylinder of radius 1.3 centimeters. So I have taken a cylinder beaker of radius 1.5 centimeters. Now find the height of water in the cylinder. Now if I convert this problem into a real life activity, then I take a cube which is filled with water until here. So till here I measure this to be a cube, and in the cube of side 3 centimeters I fill this entirely with water. Now this cube filled with water is then poured into a beaker. So I just pour this water into the beaker. Now this being cylindrical, this being bigger than this, definitely cannot have water fully filled up. Now the space or the capacity of this beaker is more. Now the question here is, a cube filled with water poured into a cylinder has some height reached. Now the question says, if the radius of the cylinder is 1.5 centimeters, then after pouring some water, the water is reached to some height. The question is about finding the height of water, not the height of the beaker, but height of water when it is poured into a cylinder. Now, how do I find the height of this water using the basic cube which is taken into consideration in the initial case? Is what is about this topic: conversion of solids from one solid structure to the other solid structure. In this case, a cube converted into a cylinder. So let's see how I can find the height of the water in this beaker, cylindrical beaker, the water which is poured from a cube of side 3 centimeters is the question out here. So let's see how we can solve this real life problem or an activity using mathematical formulae. Now let's try to convert the real life activity into the mathematical properties. So I have taken a cube on which there's water filled up totally, and once this water is poured into a cylindrical beaker, so once the water is poured in, I see that this beaker occupies water until some height. Now the question here is on how I can find the height of the water which I need to find. In this case, the question is about finding height of the level of water in the cylindrical beaker which is considered. Now once the water is poured and thus I have the dimensions 3 centimeter is the dimension of the cube, and the radius of the cylinder is 1.5 centimeters as given in the problem. The radius is 1.5 centimeters, and the question is about finding the height of the water in the cylindrical vessel. So initially what I do, I clearly understand that when this water inside the cube, exactly the amount of water filled in the cube is nothing but the capacity of the cube is poured into the cylindrical vessel, implies volume of cube is nothing but volume of the cylindrical part occupied by the water. Because this is the same water poured inside the cylindrical beaker, the volume of cube is nothing but volume of water inside the cylindrical tank. Therefore, here I have volume of cube is equal to volume of water in the cylindrical beaker. Is how we visualize when the same water is poured inside the cylindrical beaker. Now here that implies volume of cube we all know is side cube, but because the side is 3 centimeters, so volume of cube is 3 cube is how we get when we substitute the formula for volume, side cube. Similarly, volume of water in the cylindrical beaker is nothing but volume of cylinder as formed by the water. We do not consider the volume of the cylinder which is occupied in air, but we consider the volume of cylinder which the water forms. So only the water part is considered, that is volume of cylinder as formed by the water is the only volume which is considered in the cylindrical beaker, because this is the water poured in. Air is diluted. Now here this implies volume of cylinder we know is 1 by 3 pi r square h, if the height of the water is h and the radius is 1.5 centimeters, then the volume of cylinder occupied as in the water region is 1 by 3 is pi r square h, or pi r square times h is what we get when we simplify this. So proceeding from this, I get an equation which is 3 cube equals pi, as we take as 22 by 7 times 1.5 whole square. I can write 3 over 2 whole square times h, because 3 by 2 is 1.5. I write this because the next step would be 22 by 7 times 3 square by 2 square, or 4 times h. This on further simplification cancels one of the 3, and I get 3 is 22 by 7 times h by 4, which on further simplification gives, on cross multiplication gives 7 2s 14 times 3 over 11 is what I get the height on cross multiplication. This on further simplification gives 42 over 11, which gives me approximately the height of the water occupied in the cylinder, in the cylindrical beaker, that is 11 3s 33, 90, 11 8s 88, 20, and 11 1s approximately 3.81 centimeter is the height. So the height of the water as occupied is 3.81 centimeters of the beaker. Therefore, if I take the real life activity, then I assume that approximately the height of the water in the beaker is 3.8 centimeters when I pour the water from the cube into the cylinder. Conversion of one solid into another solid helps me in finding the volume of water inside the cylinder using the volume of cube. This is how we understand mensuration when we go deeper into the concepts, a real life application of mensuration.